Hi, welcome to week 6, chapter 6 of quantitative methods. Today we will cover continuous probability distributions. Last time we covered discrete ones. So just a quick recap. Last time we studied binomial distributions and Poisson distributions. They were rules which warranted which ones to use. So the learning objective for today is we will solve for probabilities in a continuous uniform distribution. Remember, continuous. There are two points between. There's a point between 2 points, and then between the next 2 points, there's another one, and it keeps on going. So it's a very, it's an infinite space. Okay. So we'll solve for probabilities in a continuous uniform distribution. We studied what that is last time. We will solve for probabilities in normal distribution, bell curve, using z-scores. So we will discuss what z is. And for the mean and standard deviation, or a value of x in a normal distribution when given information is about the area under the normal bell curve. So if you don't understand what this is right now, you will by the end of this lecture. Then we'll try to solve a problem from the discrete binomial distribution using the continuous normal distribution and correcting for continuity. So what are continuous random variables? Like we discussed last time, age is a continuous random variable. You can say I'm 10 years old, or 10.2 years old, or 10.235678905, whatever. And the precision goes to infinity. Similarly, another random variable is your height or time. They're all random continuous variables. So continuous random variables take values in a given interval. The probability of any exact outcome would be 0, since it's one of indefinitely many values. So how many numbers between 0 and 1? If I say my increments are 0.1, so 0.1, 0.2, 0.3 up till 0.9 and 1.0. But this is not what continuous random variables are. Between every two numbers, there's another number. And then every two numbers, there's another number. So in a range, what is the probability that exact 2 will come? You don't know. Okay, 0. Because 0 because 2 as compared to an infinite number of combinations is close to 0 chance. Okay. So continuous random variables do not have probability mass function. Instead, they have probability intervals. And we will understand that as we go along in this lecture. So let's have an example. We have temperature. Excuse me. You measure temperature in Perth at noon, it could be 27.4 degrees. Or if you have a very decent thermometer, it can be 27.41 degrees Celsius. Or maybe you have an even better thermometer and it says it's 27.412 degrees Celsius. But the values are actually infinite. Okay, you can go to any decimal place as you want. So asking for probability of exactly for 27.412 degrees Celsius does not make sense. The probability is 0. But asking that what is the probability that the temperature will be between 27 and 28, that is meaningful. So you are looking at a range now. You can say what is the probability that tomorrow's temperature will be less than 33 degrees. That is also doable in continuous random variables because it's again a range. So time to complete a task. Imagine assembling a toy takes 10 to 15 minutes. So you have many pieces of a toy or maybe a Lego, and you take that Lego and you make that toy from that Lego. Now between 10 and 15 minutes, there are infinite time possibilities. 10.1, 10.11, 10.111, 10.112, whatever, right? It's infinite number of possible combinations. You don't ask what's the chance it takes exactly 10.12345 minutes for you to make this toy. What you ask is What are the chances that it takes 12 to 13 minutes for you to make that toy? And then that is meaningful. So think of throwing a dart at a ruler, and there are infinite points on a ruler: 1 inch, 1.4 inch, 1.5 inch, 1.55 inch, 1.5678 inch, and so on. You can't hit exactly a millimeter, but you can hit between 2 and 4 centimeters, which is a measurable interval. So this is how we measure continuous random variables. Now, some terms: probability density function and probability mass function. Let's see what these are. These are important terminologies. They are mentioned throughout in literature and in every paper and most of the statistics books. So let's just see what that really means. One is used for discrete variables, the other one is used for continuous variables. So the probability density function PDF or probability mass function PMF are both ways to describe the distribution of probabilities. They apply to different types of variables. Remember the dice function? We roll 2 dices and then we plot how many times did I get 2, 3, 4, 5, and we saw that that diagram had 7 as the highest bar. That was a probability mass function, because either a dice is 2 or 3, the sum of 2 dices, or 4 or 6 or 12, nothing else. So you roll 2 dices, you can never get 4.5, because either it's 4 or it's 5, right? So that is discrete. So we describe that as a probability mass function. So the distribution of the dice, let me see if I can find it. And I can show it to you guys. Here we go. So you see this image? This is the probability mass function, because you have a probability that 2 will come, or a probability that 7 will be the result if you roll 2 dices. Nothing between 7 and 8, nothing between 6 and 8. So that's why we can say, we can draw this, and this is the probability mass function. Probability mass function tells you a story that when you keep on rolling dices, this is the probability that 7 will come, or 2 will come, and 3 will come, and so on. So probability mass function, that's what it is. Now the probability density function is when the variables are random. So let's see what these two things apply to. Probability mass function, as we said, it applies to discrete random variables. Probability density function applies to continuous variables. The probability at a point, so it is specific value. So probability that x will be 2 is 30%. Okay. Probability at a given single point is 0 for a probability density function. The total probability for both is 100%. Example variables are number of heads in 10 coin tosses. And the probability density function is height of a student, or time taken to run a race. The notation is capital P, x is equal to x, and this small f is the probability density function of x. X is the random variable, continuous. So example distributions are Poisson, binomial, geometric for discrete. We studied all of them last time. And the probability density function, the distributions are normal, exponential, uniform. This is for the continuous version. So simple analogy is the probability mass function is like counting apples. You can count 10 apples or 5 or 6 or 12. You can count how many outcomes and their probabilities. And PDF is like pouring sand. You can't count the number of grains, but you can talk about the amount of sand in a region or area under a curve. Okay. So things will get simpler as we move along. So let's dive deeply into this probability density function. This f of x is for continuous random variable x, and it is a function. So continuous random variable x is a function that satisfies the following three things. It is greater than 0 for all values of x. The total area under the curve is always 1 or 100%. And the probability that x will fall between a and b is the area under the graph between x is equal to a and x is equal to b. So if I just show this to you guys. So this is a continuous random function. You see that there are no bars here, f of x. So if I say what is the probability that the value of x will be between a and b, this is a, this is b. It is actually the area under this curve. The area of the entire curve is 1, and let's say this is 38% or 40%. So the probability that the value of x will fall between a and b is 40%, and you have to integrate and get this area. Okay, so the probability that x value will fall between a and b is area under the curve between x is equal to a and x is equal to b. Okay, so what really is it? This function is used to describe the likelihood of a continuous random variable taking values in a given range. So how do you calculate that? If the range is from here to here, it's very small probability. But if the range is from a to b, look at the area under the curve. The whole area is 100% or 1. If this is 80%, then the chance of x falling randomly between a and b is 80%. Now probability density function must always be greater than or equal to 0 for all values of the variables. The total area under the entire curve is always 1, and we know that the possibility that the value of x will fall randomly between a and b is area under this curve. So imagine a task that always takes between 10 and 20 minutes to complete. Every time between 10 and 20 is equally likely. Let's say you're ironing your shirt or something, it takes 5 to 10 minutes or whatever. So this is a uniform distribution over the interval from 10 to 20. The height of the density function must be 1 divided by the width of the interval, which is 10. So the height is 0.1. The graph of this PDF looks like a flat rectangular line. I'll show it to you in the next slide. So if we look at this, so from 25 to 30, since all the chances of 20 and 20, 40 and 30, 35 and all the random things, it's between these, same chance, then this is the distribution. It's called uniform distribution. So the chance of that value falling between 25 and 30 is really 5 multiplied by the height of this box. Simple rectangle, right? But this area has to be 1. So if the width is 20, 40 minus 20, then 1 divided by 20 is the height, which is 0.05. Okay. So the total area under the graph is 1, and that's how we calculate the area under this curve. Total area under the PDF must be 1. The rectangle base is actually 20. So the base is actually 40 minus 20 is 20. So 1 divided by 20 is really 0.05. That's how we get to it. Okay. If a variable x is uniformly distributed between values a and b, it means that the value of x will always lie between a and b. It can be a or something between a and b or b. Every value chance of occurring between a and b is equally likely. So the probability density function is a flat line with height 1 divided by b minus a. How did we get that? This is b 40. This is a 20. So 40 minus 20 is really this length. So if you want area is equal to this into this, right? You want the height. So the area is 1. Area divided by this side will give you the height. Okay. So let's have a look at an example. A machine completes a task in some time between 20 to 40 minutes, and all times are equally likely. So x is a uniform function, u is the uniform function symbol that ranges uniformly between 20 and 40. So x is a uniform function that ranges between 20 and 40. The height, we know that since the area has to be 1, area is equal to height into width. We know the width, we don't know the height, so the height must be area divided by width. So 1 divided by the width, because 1 is the area, is the height. It's 0.05. So what is the probability that the task takes between 25 and 30 minutes? Very easy. 25 and 30, that's 5. 5 multiplied by the height, that is the total area under this curve. So 0.05 into 5. Okay. That gives you the answer. So 5 divided by 20. Okay. So So the answer is 0.25. You can do it like this, or you can say this width multiplied by the height, which is 5 multiplied by 0.5 is 0.25. This is exactly the same thing as multiplying this by this, but you're just comparing this height with this width with this width, because the height of both is the same. Okay. So there's a 25% chance the task takes 25 to 30 minutes. So the uniform distribution, cumulative distribution function is denoted as function of x is equal to probability that x will be less than x, or a value. So for a uniform distribution that spans between a and b, the cumulative density function is given by function capital F of x, with 0 x is less than a. This thing if x is between a and b, and 1 if x is greater than and equal to b. So let's have a look at an example that sheds some light on this. So cumulative distribution function tells us the probability that a random number is less than or equal to a value. Okay, so less than and equal to a value means from that point and before, compute all probabilities. So if x is a uniformly distributed variable between a and b, this is a, this is b. Before a, the probability is 0. So if this is a, what are the chances of 19 occurring? 0, because it's just a flat line here. What are the probability that more than 40, anything greater than 40 will occur? 0. Between a and b, there is a probability. Okay. So at or beyond b, the probability is 1. Here, the probability of the total probability is 1, cumulative probability. Okay. So what's the chance I'll find this task in 30 minutes or less? This is 30 minutes. Less means 30 to 20. So now I'm going to take all this area. Now the base is 10. 10 multiplied by 0.05 is 0.5. 50% chances that I'll do this. And it also makes sense because this is half of this. So 30 to 40 is 10. 30 to 20 is 10. So this area should be 50%. And we just proved that it is 50% chances. Similarly, what is the maximum weight of a parcel? What's the maximum weight a parcel can have if 90% of shipments are lighter than it? And so you have all these questions that you can answer, but it's always a range. It is say this and less, this or more, or this and between this, and so on. So let's have a look at an example. Suppose the time taken for a student to complete a task is uniformly distributed between 10 and 30 minutes. So X is a uniform distribution ranging between 10 and 30. Let's calculate the probability that the task takes 18 minutes or less. Now, 18 is between 10 and 30. So 18 minutes or less means 18 till 10. 18 till 10 is actually 8. So 8 multiplied by the height, and that should be your answer. Why are we doing this? Okay. Let's see if I can draw on here. Okay, I'll draw on paint. Okay. So if we have a rectangle, let me draw a rectangle here. Just use this thing. If we have a rectangle, then this is the total base, and this is a smaller base, right? So what we are doing, if this is A and this is B, right, and this is 40, and let's say this is 20, so the formula really says that B minus A divided by total 40 minus 20. That is what the formula says. So the total width and height of the rectangle versus the width and height of rectangle. Height remains the same, right? But the two width limits we know. So height is same in this one, height is same as this one. So the height cancels out and you are left with this formula. Okay. So the probability that a student will complete this task is 18 or less minutes, range from 18 till 10, and that width multiplied by the height is really 40%. So there's a 40% chance the task is completed in 18 minutes or less. Another example, so suppose the amount of time taken to assemble a plastic module ranges from 27 to 39 seconds. It is a uniform distribution starting from 27 and 39. The probability is flat or uniform. What is the probability that a given assembly will take between 30 and 35 seconds? So now 30 and 35, you have 5-second interval, right? So 5 multiplied by the height is the answer. If you say fewer than 30, then 30 minus 27, because from 30 to 27, that is the area you're going to look at. 30 minus 27 is 3 seconds. So 3 multiplied by the height is this area, and that area should be 25%. So this is an example of a normal distribution. It is usually shown like this. Okay, this is how it's shown. This is normal distribution because it's normally distributed around 0. It has almost the same shape. So let the random variable x have a normal distribution with mean this is the mean value, and variance and standard deviation. We write x as n, which means normal distribution or a bell curve, n for normal, and in brackets we write standard deviation and variance. Mean and variance, and we know that standard deviation is the square root of this sigma. So note that the variance is given in this description. Now, let me see if I have that running. Now you recall we studied the z-score, which is the value of x minus the mean value divided by standard deviation. Okay, or you divide x divided by standard deviation, mu divided by standard deviation. So z is a function of a and b. A is a coefficient 1 over sigma, and b is mu over sigma, and x is a variable. So if we achieve this, then we call z as the standard normal distribution with the mean of 0 and a standard deviation of 1. Okay. So what we try to do is we compress these into a mean of 0 and then a standard deviation of 1, and then we can compare multiple variables of different ranges of different means, and we bring them down to the same measuring board and we can measure them across each other. So normal distribution is a continuous bell curve shape. It's used to model things that naturally cluster around an average, such as test scores or body temperatures or heights or ages. So in a country, the normal or the mean or median or mean age of males can be 70 years, and then it is distributed around that. Some very few people get to live 100, and some very unfortunate people get to live till 40, most of them, but most of the adults, they reach 70. And in some other country that may be different, so that tells you a story about age or that variable. So if a variable follows normal distribution, it has a mean and it has a standard deviation, we can write that x variable as normally distributed with a mean of mu and a variance of sigma square. Now to compare values from different normal distributions, let's say you have age and then you have salary. Salary is in thousands, age is in tens. You want to compare these two numbers, we have to standardize them. So maybe if we can somehow bring their means to 0 and their variances, so standard deviation to 1, we can compare them. So to compare from different normal distributions, we use a z-table. So we standardize both variables using the z-score formula, and the z-score formula is x value minus mu over standard deviation. So every value of x is converted like in a z-score. So this transforms any normal variable into a standard normal distribution, and that z we say is normally distributed between 0 mean and 1 standard deviation. Okay, one variance, one standard deviation. So the mean is 0 and the standard deviation is 1. We can also reverse this to go from z back to x. How? Sigma multiplied by z plus mu is your original x value. So these spaces are interchangeable. For example, suppose exam scores are normally distributed with the mean of 70 and the standard deviation of 10. Now I may have an exam that is worth 200 points, one exam that is worth 5 points. How do I compare them both? Their averages are different. So if we can compress them both into z normal, we can compare them because both means will be 0 and standard deviation will be 1. So suppose exam scores are normally distributed with mean 70 and standard deviation is 10. That's how it looks like. Question is, what is the z-scores of a student who scored 85? Okay, so x value is now 85. We know that mu is the standard is the mean divided by 10. So your z-score is 1.5. Now what that means is that a z-score of 1.5, the student is 1.5 standard deviation above the average score. Okay, so that's what it means. Using the standard normal distribution table, we can see that if the value of z is 1.5, then that is a value of 9.9332 or 93.32%. So that student is above 93.32% students. So a score of 85 in this example has a 1.5 standard deviation above the mean. That is what it means. Now, let's have a look at different types of normally distributed graphs. Some are clustered around the zero, some are not. So they may have different means. This has a mean 0. This has a mean 1. This is a mean 1, the -1. All these have the same mean, but they have different standard deviation. The black one has 1 standard deviation. The dotted red has 2 standard deviation. It is spread across this mean. Okay. So this is an example of different means and different variance or standard deviations. So z-score tells us how far a value from the average. If z-score is 0, you are sitting at the average. So if you took an exam of maximum 10 points or you took an exam of 1,000 points, then the both exams average is calculated and your score is computed and a z-score is calculated. And if you have 0 in both, z-score 0 in both, you are exactly sitting at the average of both tests. Similarly, a z-score of 1 means that you are 1 standard deviation above the average, and a z-score of -2 tells you that you are 2 standard deviations below the average. And this is the formula that we calculate the z from. Z is a very, very important tool as a mathematician and a statistician. So please make sure that you understand this very, very thoroughly. Now, the normal distribution defined by mean and standard deviation, the notation is this, if you remember. So n for normal, mu is the mean, this is the variance. So example is height of people might be normally distributed with mean at 170 centimeters and first standard deviation is 10. Okay. So the standard normal, what we will try to do is we'll say, okay, if mean is 170, then we will calculate the z, and when z is 0, it really means 170. But then everybody is compressed to a range of 0 and standard deviation of 1 and 2 and 3 and so on. So normal distribution and standard normal distribution, the mean is any real number. In a standard normal compressed by z, it is 0. Standard deviation is any positive number in normal distribution, it is 1. The notation is x is really normally distributed with a mean of this and variance sigma square, and z is really normal with a mean of 0 and a standard deviation of 1. Where are they used? Normal distribution describes real world data. So the average weight of males between 40 and 45, the average sugar or intake of a child between 5 and 6 years old, right? That is normal distribution. But use case for standard normal, it is used to calculate probabilities via z-scores. You have tables generated, you find the z-score, you look up a table and you say the probability is 60% or 80% or whatever, because the z-scales are very predictable. Okay. So what is a z-table? It is a chart that shows the probability of a z-score being less than a given value. So you say, hey, what is your score in z? You say my score is 1.5. So then we look at it and look at a z-table and see how many people are below you. So it tells you how much area or probability lies to the left of the z-score under the standard normal curve. Why is it useful? Because you can convert any normal distribution into a standard one using z-score formula. And then the z-table helps you in determining or asking or answering questions. For instance, find the probabilities of values. Example, what are the chance a person scores less than 85? Okay. Find value of given probabilities, for instance, the score corresponding to top 10%. So you can answer all these questions. Okay. So I think this, did we? Okay. So what is a z-score? Imagine a math test. The average score is 70, standard deviation is 10, student got 85. That student's score is 1.5. So a score of 85 has a z-score of 1.5, meaning that it is 1.5 standard deviation above the average. Okay. And what does it tell you? The z table, when you look at it, it tells us that the probabilities that a value is less than a certain z-score. So what is the probability that values are less than a certain z-score? If you look up 1.5, z is equal to 1.5 in a z table, it says 93.32%, which means 93.32 students scored less than you because you got 85. Or in other words, the students who scored 85 are in the top 6.68%, or in the yellow zone. So to summarize, z-score is how far a value is from the mean. It can be in the positive direction. It can also be in the negative direction. Z-table is how much area probability, which is probability, is to the left of that z-score. And then you can subtract it from minus to get the right hand side. Okay. So this is why we convert to z, so we can use the same table for any problem, no matter what the mean and standard deviations are. Now, here's a summary of what we just learned. So z-score, how far a value is from the average or mean, measured in standard deviations. One means you are one standard deviation away. So if the standard deviation is 3.5, you are 3.5 away from the mean. The formula of z is this. The example is test average is 60, you scored 75, standard deviation is 10, z score is 1.5. Interpretation, how do you interpret that? Your score is 1.5 times the standard deviations higher than the mean. And z-table gives you that. So z-table gives, for 1.5 score, 1.5 standard deviation, it gives you 93.32 scored less than you. Now, how do we, let's try to solve a problem. So a z-table lists cumulative probabilities for a standard normal. If you have z1, then at that point, what is the area of curve behind it, or from that point towards the left? That is what the z-table tells you. Now, why is normal distribution important? Because if this is the mean and this is one standard deviation, then one standard deviation covers about 68% of the area. Two standard deviations cover 95% of the probability. Three standard deviations cover 99% of, actually 2.5. Yeah, 2.5 cover about 99% of the times. So if you are, if your z-score is 3, it is about 99.99% of the times that you are covering. And we'll get to that in a minute. So using a z-table, this is how a z-table looks like. Let's say for a value of 1, let's say you want to say I scored z is equal to 1 from the mean. So this is mean, this is 1. And then this z-score tells you, you say, okay, just have a look here. And it says, hey, the value is, if z is 1, from 0 to 1, the value is 30%. This is 0, right? From 0 to 1, the z-score value is 0.3413, or this brown area is 34.13% of the entire area. Okay. What if you want to say less than 1? So this brown area, sorry, z less than 1, 1 from here till 1, from here till this area. So you want to compute all this area. Now it is really easy because we know that since this is uniformly or normally distributed, half of it is 0.5 and the other half is 0.5. So if you can find this brown area, then to find from 1 till this, you just have to add 0.5 to it. So 0.5 plus this area becomes 0.8413. So if you want to say I scored 1, how many people scored less than me? All this area. So this z-score plus 0.5 is 0.8413, or 84.13 people scored less than you. So that's how we read this diagram, and I just showed you how. So in the example we have, if you want to find the probability that z value is greater than 1, then 1 minus all the values where z is less than 1. So this is all the values where z is less than 1, and the whole graph is 1. So 1 minus this entire thing is actually this small area. So the question that what is the probability that a student's score will be greater than 1, z1, this. What is the probability that the score will be less than, so this is a typo, less than 2.51, or z is greater than 2.51, then 1 minus p into z minus z is less than 2.51. So this becomes a larger or smaller area. So that is the end of today's lecture, and please try to do the exercises that are given for this week. I will see you all in the new year, and I'll in face-to-face lectures. So yeah, good luck.